Hi, this is Puro Badani, an assistant professor at the Department of Chemistry, University of Mumbai. Today, I'll be discussing with you all the very important topic in chemistry, that is catalysis. At the onset, let us try to understand what is a catalyst. Catalyst is a substance which, when added in a chemical reaction, it increases the rate of a chemical reaction without undergoing any permanent chemical change. It works by lowering down the activation energy of the reaction. What does this mean? It means that suppose if you are performing a chemical reaction where you are interested in converting the reactant A into product B. In that particular case, if you try to draw a graph of the progress of a chemical reaction, the progress of a reaction against relative energy, what you would observe is you would have reactant A having certain relative energy. Let me say you are trying to form the product B having energy slightly lower as compared to that of A, and you want to convert reactant A to product B. In that particular case, you need to supply certain energy to a chemical reaction so that it can cross the barrier. The energy required to cross this particular barrier is referred as activation energy. Let me abbreviate it with the symbol EA. So as you can see in this particular case, in absence of any external catalyst, in order to convert reactant A to product B, you need to supply an energy equal to EA, that is nothing but the activation energy associated with that particular transition state. Now, suppose if you are in this particular reaction, if you are adding an external catalyst, let me say C. In that particular case, what happens is when you add an external catalyst, in that particular case, the energy required to cross the barrier decreases. So an alternative transition state, that is TS hash, is getting generated. This transition state allows us to perform the chemical reaction at a lower activation energy, which has been represented by blue dot. In this particular case, the activation energy required to perform a chemical reaction is equal to EA dash. As you can see, in this particular case, the energy required for performing the chemical reaction in presence of a catalyst, that is EA dash, is less than EA, that is energy required to perform the same chemical reaction in absence of the catalyst. So what exactly is the catalyst doing? Catalyst is providing an alternative reaction path such that it is lowering down the activation energy. And since the activation energy is lowered down, the rate of a chemical reaction increases. So this is how we get the definition of catalysis. So again, let us walk through the definition of catalysis. Catalyst is basically a substance that increases the rate of a chemical reaction without undergoing any permanent chemical change. It works by lowering down the activation energy. It works by lowering down the activation energy. It is very important to note over here that a catalyst itself will never undergo any permanent chemical change. It means that at the end of a chemical reaction, your catalyst will be regenerated. Now let us understand what are the important properties of a catalyst. The very first important property of a catalyst is that it lowers down the activation energy of a chemical reaction. So as discussed earlier, if you perform a chemical reaction in absence of a catalyst, the reaction is still going to occur, but with a higher activation energy. So what is the job of a catalyst? The job of a catalyst is to provide an alternative reaction pathway so that the activation energy of a chemical reaction is lowered down. Second important property of a catalyst is it will never undergo a permanent chemical change. It means that at the end of the reaction, your catalyst will be regenerated. Next important property of a catalyst is it does not affect the equilibrium of a reaction. That is, it speeds up the rates of forward as well as backward reaction. Now, what does this mean? Let us try to understand this again with the diagram similar to what we used in the previous slide. The next important property of the catalyst is it does not affect the equilibrium of the reaction. Now, what does this mean? This means that it speeds up both forward as well as reverse direction equally. Now, what does this mean? Let us understand this using pictorial representation. Now, again, suppose if I plot progress of reaction against relative energy, what did I saw? Suppose I have a reactant A, I want to convert it into product B. I need to supply certain energy so that it can cross the energy barrier in absence of the catalyst. Let me say the activation energy required in this particular case was supposed to be EA. Now for the same reaction, suppose if I'm adding a catalyst, what it does is it provides an alternative reaction pathway so that the energy required to perform the same reaction is lowered down, and in this particular case the energy required is EA dash. So as you look carefully in this particular scenario, what is happening is when you are moving the reaction in the forward direction from A to B, the energy required is lowered down in presence of the catalyst. So the rate constant of the forward reaction increases. If you look at the reverse reaction, if you want to convert from B to A, in that case also the activation energy is lowered down. So the rate constant of the backward reaction is also decreased. So what does a catalyst do is it speed up both rate of the forward as well as rate of the backward reactions equally. Now how do we define an equilibrium constant? Equilibrium constant K would be defined as rate constant of the forward reaction, that is K1, divided by the rate constant of the backward reaction K-1. As you can see in the case of a catalyzed reaction, K1, that is rate constant of the forward reaction, and the K-1, that is the rate constant of the backward reactions, are equally affected. It means that the value of equilibrium constant, that is capital K, remains constant, as same as that of an uncatalyzed reaction. I hope this is clear now that it does not affect the equilibrium because the catalyst is going to speed up both forward as well as backward reactions equally. Next point, the next important property of a catalytic system is catalysts are highly specific. It works only for a particular reaction. Let us take an example. Suppose you want to perform a reaction wherein nitrogen reacts with hydrogen to form ammonia. Let me balance this reaction. So you have 2 nitrogen, so I write down 2 over here. So eventually you have 6 hydrogen. So to balance it, I have 3 hydrogens over here. So my reaction is balanced. So in this particular reaction, this is supposed to be synthesis of ammonia by Haber's process, and the catalyst used in this particular case is supposed to be iron. Iron is a very specific catalyst which is being used for this particular reaction. No other catalyst basically can be used for performing the same reaction. So what does it mean? It means that the catalyst is very specific for a given reaction. Catalyst, next important property of the catalytic system is it is required in a very small amount. You need to add catalyst into a very small amount in a reaction system when you compare its concentration with respect to the reactants. And the last and the important property of the catalyst is they are regenerable in nature. What does it mean? That at the end of a chemical reaction, you should be able to recover the entire catalyst, because catalyst will never undergo chemical change. It will only provide an alternative pathway for the reaction to occur. It means that at the end of a chemical reaction, your catalyst will be regenerated. Now let us look for the next topic, different types of catalyst along with the example. Catalysts are broadly classified into 2 types. One is homogeneous catalyst and second is something called as heterogeneous catalyst. Now what is a homogeneous catalyst? If you have a catalyst which is in same phase as that of reactant, such catalysts are called as homogeneous catalyst. What do you mean by same phase? It means that suppose if you have your reactant molecule in liquid phase, your catalyst will also be in the liquid phase. Suppose you have your reactant molecule in gaseous phase, your catalyst will also be in the gaseous phase. So the physical state of catalyst is exactly same as that of reactant. Such catalytic systems are called as homogeneous catalysts. What is a classic example of this? The classic example of a homogeneously catalyzed reaction is hydrolysis of ester using sulfuric acid. Suppose if I consider an ester like CH3, COO, CH3, that is methyl acetate. If I undergo an hydrolysis of this particular methyl acetate, so in presence of water, suppose if I add sulfuric acid as a catalyst, that is H2SO4, methyl acetate would undergo hydrolysis to form CH3COOH plus CH3OH. So I get acetic acid and I get methanol. So in this particular case, if you look carefully, your methyl acetate is in the liquid state, your water is anyways aqueous, it is in liquid state, and your sulfuric acid is also in the liquid state. The physical state of all the reactants and the catalyst is same, so sulfuric acid is referred as a homogeneous catalyst for this particular reaction system. Against homogeneous catalyst, what we have is a heterogeneous catalyst. What is a heterogeneous catalyst? A heterogeneous catalyst have a different phase as compared to that of the reactant. What does it mean? Suppose you have your reactant in liquid phase, then your catalyst will not be in the liquid phase. It can be in the solid phase. Suppose you have your reactant molecule in the gaseous phase, then your catalyst will not be in the gaseous phase. It can be in the liquid phase or it can be in the solid phase. Such systems are called as heterogeneous catalyzed system. And the classic example of this is supposed to be synthesis of ammonia using Haber's process using iron as a catalyst. So in this particular case, you have nitrogen. It chemically reacts with hydrogen to form ammonia in presence of the catalyst, that is iron. If I balance this reaction, I add 2 over here. There are 6 hydrogens there on the product side, so I add 3 on the reactant side, so the total hydrogen is now balanced. So if you look carefully in this particular case, you have your reactant nitrogen in the gas phase, under reactant hydrogen which is also in the gas phase, and you have your catalyst which is in the solid phase. So the physical state of reactants and catalyst is different, and such systems are called as homogeneous catalyzed reactions. Now let us try to understand the difference between a homogeneous catalyzed reaction and a heterogeneous catalyzed reaction. So what is the definition of the homogeneous catalyzed reaction? As discussed in the previous slide, if the catalyst and the reactants are in the same phase, then they are called as a homogeneous catalyzed reaction. On the other hand, if you have catalyst and the reactants in different phase, then they are called as heterogeneous catalyzed reaction. So in a homogeneous catalyzed reaction, the reactants and the catalyst will be in the same phase, that is, they will be liquid-liquid or they will be gas-gas. On the other hand, when you compare the phase of the catalyst with respect to the reactants, they will be different. So you can have a solid catalyst with liquid reactants, you can have a solid catalyst with the gaseous reactants, and so on and so forth. The most common reaction medium in a homogeneous catalyzed reaction is either solution or it is a gas. In this case, again, to reiterate, you will have a catalyst which is also either in the solution phase or in the gaseous phase respectively. In case of a heterogeneous catalyzed reaction, the most common reaction medium is supposed to be the solid surface catalyst. The surface of a solid catalyst is the most common reaction medium. Now, when you compare the absolute rate of the reaction, generally it has been observed that the homogeneous catalyzed reaction are relatively faster because it involves molecular level interaction. On the other hand, heterogeneous catalyzed reaction are relatively smaller because it is controlled by the diffusion process. You need to physically adsorb your reactant molecule on the catalytic surface. which makes the process relatively slower. As far as the catalyst recovery is concerned, in the first case, that is in the homogeneous catalysis, it is difficult to separate reactants and catalysts because they are in the same phase. So it's a bit of a challenging task to separate your reactant and your catalyst. On the other hand, in case of a homogeneous catalysis reaction, since the physical state of a reactant and the catalyst is different, they are easy to separate and they are very easy to reuse. Homogeneous catalyzed reaction offers a very high selectivity. That's a major advantage of the homogeneous catalyzed reaction. And the major advantage which is offered by the heterogeneous catalyzed reaction is they are very easy to control and they are very widely used for industrial process. I hope this distinction between homogeneous catalyzed reaction and the heterogeneous catalyzed reaction is clear. Now, let us explore the next important property of the catalysis. The two crucial property of the catalysis is specificity and selectivity. As discussed in the earlier slide, catalyst plays a very crucial role in a chemical reaction by influencing the rate of a chemical reaction and directing the product formation. The two most important properties that catalysis offer is supposed to be in terms of its specificity and in terms of its selectivity. Now let us understand what is meant by specificity of a catalyst and what is meant by selectivity of a catalyst. As the name suggests, specificity, a catalyst is called as specific when it catalyzes only a particular reaction or a type of a reaction. So if a catalyst catalyzes only a particular reaction or a type of a reaction, then such catalyst is called as a specific reaction. Mind well that such catalysts do not work for other reaction even if they are similar reactions or there are similar reaction conditions. They are not going to work. On the other hand, what is meant by selective catalyst? A catalyst is referred to be selective when it directs a reaction to form a specific product. Again, repeat. A catalyst is selective when it directs the reaction towards formation of a specific product, even if there is a possibility of formation of multiple products. So theoretically speaking, different products could have been formed, but catalyst would allow formation of only one specific product. It is important to note over here that different catalysts can form different products. But once you select a specific catalyst, it is going to always form a specific product. Such catalysts are called as selective catalysts. Let us understand this by taking few examples. Now let us first talk about specificity of a catalyst. As discussed in the earlier slide, how would you define a specific catalyst? That it works only for a particular reaction. Let us consider examples. Consider an example of urinase enzyme. Now, you use a urinase enzyme for the hydrolysis of urea. What you're going to get is ammonia and carbon dioxide. So urea on hydrolysis in presence of urease as a catalyst is going to give you ammonia and water. Mind well, this particular catalyst will only bring about urea hydrolysis. It will not bring about hydrolysis of any other amide like acetamide or any other amide you talk about. Urease enzyme will not catalyze this reaction. It's going to be very, very specific only for the hydrolysis of urea. Let's take another example. Use of iron as a catalyst in the Haber's process for synthesis of ammonia. So this reaction we have already discussed earlier. You have nitrogen reacting with hydrogen to form ammonia in presence of iron as a catalyst. In this particular case, iron specifically catalyzes the synthesis of ammonia, but it will not catalyze formation of nitrogen product under same condition. It will not catalyze the formation of any other nitrogen product under the same conditions. There is a very, very specific catalyst for this particular reaction. Likewise, suppose you talk about hydrogenation reaction using platinum as a catalyst. Suppose you are taking C2H4, which is supposed to be an alkane, you hydrogenate it to form an ethane, so you are doing an hydrogenation reaction. In this particular case, you are using platinum as a catalyst. So platinum is very specific for hydrogenation reaction. It will be very useful to use platinum surface for hydrogenation reaction, but it will not work for any other reaction. This classifies or it qualifies a platinum to be called as a very specific catalyst for hydrogenation reaction. I hope with this example, the concept of specificity of the catalyst is clear. Now, let us understand what do you mean by selectivity of a catalyst. As discussed in earlier slide, how do we define selectivity of a catalyst? A catalyst is referred to be very selective in nature when it directs a reaction to form a specific product. When a specific product is formed, then such catalysts are referred as specific catalyst. Let us take an example. Now, if you look in this particular case, example, when we talk about hydrogenation reaction, in the very first example, you take an alkyne and you use nickel as the catalyst, what you're going to get is supposed to be an ethane. So in this particular case, nickel basically performs complete hydrogenation of alkynes to form alkanes. On the other hand, you use Lindlar catalyst, it is used for partial hydrogenation of alkene. It is used for partial hydrogenation to alkenes. What does it mean? It means that in this particular case, if you have a reactant that is alkyne, in presence of hydrogen and Lindlar catalyst, what you are going to get is supposed to be an alkene, that is partial hydrogenation. So look over here. Nickel is a selective catalyst for complete hydrogenation, and Lindlar catalyst is a very selective catalyst for partial hydrogenation. So depending upon what is your end product, you decide what catalyst you want to use. Let us take one more example. Let us talk about oxidation of ammonia. Oxidation of ammonia can result in formation of multiple products. Now suppose you are performing oxidation reaction of ammonia in presence of platinum as a catalyst, what you are going to get is nitric oxide as your product. I again repeat, suppose if you are using ammonia, you are performing the oxidation reaction of ammonia in presence of platinum as a catalyst, what you are going to get is nitric oxide as your product. This is in presence of platinum as a catalyst. The oxidation of same ammonia in presence of vanadium oxide is going to give you nitrogen as a product. So the oxidation of ammonia technically can result in formation of multiple products. But depending upon what catalyst you use, you can direct the product formation. In case of platinum as a catalyst, you are selectively forming nitric oxide. So as you can see in this case, when you perform the oxidation of ammonia, there is a possibility of formation of multiple products. But in this particular case, depending upon the catalyst that you use, you can direct the product formation. If you are using platinum as a catalyst, oxidation of ammonia will result in formation of nitric oxide. On the other hand, in presence of vanadium oxide as a catalyst, oxidation of ammonia would result in formation of nitrogen. I hope this is clear. With this, we have understood, in this particular lecture, we have understood some basic concepts of catalyst. We have understood what is meant by catalyst, how does catalyst increase the rate of a chemical reaction. We understood different types of catalyst, that is homogeneous catalyst and heterogeneous catalyst, as well as we understood and we explored two important properties of catalyst, that is selectivity and specificity. In the next lecture, we'll talk about additional aspects of catalyst. Thank you.